All right, continuing our discussion of alternating series, and specifically the alternating series test. Example 1 asks us to determine whether the series converges or diverges. So when you see something like a -1 raised to some sort of power in your series, unless it's geometric, the only thing that you have to go with is your alternating series test. So let's give it a try. So, looking at our alternating series test, remember that we are able to apply it when our term without the alternator is positive, is greater than 0. Whoa, too far. All right, so for us, our term is, hey, what's going on? Our nth term is equal to 1 over n. Well, 1 over n, that is definitely positive for n greater than or equal to 1, right? We know that because it starts at 1, goes off to infinity. All right, so now I'm going to check the two conditions. The first one I always check is the limit, because if the limit is usually the easier part of this anyway, and if it fails, then you're done with the test, and you probably switch to the nth term test for divergence and show that it actually diverges. So let's see. I'm going to take the limit as n approaches infinity of 1 over n. You leave this part off of it. Boop. You just get rid of it, right? And that, sure, definitely approaches 0. 1 over infinity, yeah, that approaches 0. So check for the very first part of our test. Now the second one, what I'm supposed to do is show that the n plus 1th term is less than or equal to the nth term. In other words, our terms are decreasing. I can show this either algebraically or calculistically. I'm going to do it algebraically, which means that everywhere on this left-hand side, everywhere I see an n, I plug in an n plus 1. I would have 1 over n plus 1. Is that less than or equal to 1 over n for the nth term? Well, maybe it's obvious to you that that inequality is true. Maybe it's not. One way to be able to tell is just to simplify it, cross-multiply. Now, when you have an inequality, you have to be careful when you multiply, because if you multiply by a negative, it's supposed to switch the signs. I don't have to worry about that in this case because we're talking about n and n plus 1 over here. Whoops, yeah. N and n plus 1, and starting at 1, going off to infinity, I think that we're okay. We're going to be dealing with only positive numbers. So when I cross multiply this n up to the top, I'd have n is less than or equal to n plus 1. Okay, if that's not obvious enough for you, subtract n from both sides, and I'd have 0 is less than or equal to 1. Oh, yep, that's definitely true for all values of n. So that's good. So this is, dang it. So this is true for, I just need it for n greater than or equal to 1. So it checks off. Both conditions are met for the alternating series test. So I'm just going to point that out in my conclusion. I'm going to say, since the limit as n approaches infinity of 1 over n equals 0, and 1 over, that's an and, 1 over n plus 1 is less than or equal to 1 over n for n greater than or equal to 1, I can conclude that the series from n equals 1 to infinity of -1 to the nth plus 1 times 1 over n converges by the alternating series test. All right, so take a sec to absorb what we were just able to prove. This is the alternating harmonic series. Alternating harmonic. In the alternating harmonic series, as we were just able to demonstrate, it converges. The harmonic series by itself diverges, but if we alternate the signs, we take enough away that it actually is going to approach a particular number. I wonder what that number is. It's a good question. Okay, well, let's try another one. Back to the slideshow here. I think I have a couple of things that may be highlighted here. Yeah, it's all of the math that we just were able to show. Dub, dub, dub. Yep, that's also true. And then we have some images over here of the individual terms in blue down below, and then their corresponding partial sums up above. So you can see that the individual terms of the sequence are approaching 0. They're decreasing towards 0. Okay. And then if I add them up, they're adding and subtracting. Sure, they're alternating, but they're getting closer and closer to some number. And it looks like that number is something less than 1. Whoop, right there. Okay. That's the alternating harmonic series, which totally converges by the alternating series test. On example 2, determine whether this series converges or diverges. I got negative 1 to the nth times 3n over 4n minus 1. And since it alternates and it is not geometric, I'm going to use the alternating series test. So as far as this goes, my nth term is equal to 3n over 4n minus 1. And my n here is greater than 1. It starts at 1. It's greater than or equal to 1. On the top, that would be a 3 or bigger. And on the bottom, that'd be 4 minus a 3 or bigger also. So that means that this is always greater than 0. Check. All right. So now I want to check my two conditions. The first one being the limit as n approaches infinity. I take off the alternator and I go 3n over 4n minus 1. If I plug in infinity, I get infinity over infinity. This looks like L'Hopital's rule, except I don't really have to do that. I could use pre-cal and go, hey, this thing approaches 3/4, which is just the ratio of the two leading terms since they have the same exponent there. Oh, yeah, but I got a problem. That's not 0. That means test fails. All right, if the test fails, there's no point to doing the second part of it. Instead, you revert back to just the nth term test for divergence. And that's not really what we did here. And the reason why it's not is because we left off the alternator. Let's put the alternator on there now. So if I take the limit as n approaches infinity of negative 1 to the nth power times 3n over 4n minus 1, well, we know that without the alternator, so just ignore this part right there, that these terms are approaching 3/4. But then as n approaches infinity for the alternator, it's going to switch back and forth between plus and minus, plus and minus, plus and minus. So in other words, the terms of this sequence are approaching adding 3/4, subtracting 3/4, adding 3/4, and subtracting 3/4. You're never ever going to zoom in on a particular number, and therefore this limit does not exist due to oscillation. And since we're oscillating, it's obviously not 0. Therefore, this series diverges by the nth term test. The nth term test for divergence. All right, so that's basically the technique that you'd want to do. If you do find that one diverges, you stop the alternating series test and then go back to the nth term test for divergence and see what you come up with for that. All right, so we're going to, in the next video, take a look at some pro tips and maybe look at another example.